So no questions from any of the previous topics?
Ma'am?
Yeah.
I have this will it work the same way for a loop as it works for normal branching?
I mean, loop is a branch as far as the instruction set is concerned. So delayed branch is basically that you have a branch and it takes more than, I mean, like you can't know the, what should I say, you can't know the outcome of the condition as well as the target address in the very next cycle, right? Essentially, basically in the next cycle, you'll fetch the next instruction. You fetch the instruction, which is a branch instruction. In the next cycle, you do the decode. Even though the MIPS implementation the book talks about finishes everything related to the branch in the decode cycle itself, which is anyway not going to happen in a real life processor. Even then, the instruction you fetch immediately after the branch instruction is usually the sequentially next instruction, right? So you don't know. Therefore, if you don't know, you should be stalling the processor. That is the delay slot, right? Now, the delayed branch means that you are trying to bring an instruction into that slot, which will be executed always. Okay. Now, therefore, if you if you can bring an instruction which occurs before the branch into the delay slot, it's a beautiful solution because it should have been executed anyway before the branch. And, so therefore, it will always be executed as per the program order. You just rescheduled it to have, be executed in the delay slot. So that's a perfect solution because that slot will never be wasted. However, it's not possible under all conditions. So you do fill the delay slot with either, taken branch sequence, right? So if you take the branch, what would be the next instruction? That would be the one which will be filling the delay slot, or the not taken instruction will be filling the delay slot. And if you fill it with the not taken instruction, but your branch is taken, then yes, you have to, convert that instruction into a NOVA. So that's the problem there. So it doesn't eliminate stalls in all cases, but if you can predict your branch properly and fill the slot properly, then your delayed branches will still, improve the performance. That is the purpose. But as we have seen, um, if there's only one delay slot, makes sense and it's easy to find an instruction to fill into that slot. But if the branch in real life processors is actually evaluated at the end of some 5 or 10 cycles, then you can't possibly fill 5 or 10 cycles with delay some other instructions. So the only solution in these cases is branch prediction. And as we have seen in the previous class, the branch predictors are extremely complex, and they do a lot of good percentage of predictions, right? Something like about 90% prediction accuracy is there in branch predictors. So it helps to reduce the stalls due to branches. When we come to the next part of the course after today's class, we'll see how branch issues are resolved even further through what is called as speculation. So they try to eliminate all performance losses due to branches. Otherwise, in regular programs that we see, not the scientific programs, but the regular programs that we see, there are a lot of branches. Every 5 lines of code or something, you will come across a branch. And if branches are not handled, then there cannot be any performance improvements. So one of the techniques is delayed branch for very low-end processors. Branch prediction, complex branch prediction in the real-life processors, that regular processors we see, but it is also combined with other hardware improvements to eliminate performance issues.
Yeah.
So looks like others are not going to join, since only 11 are there, and 11 including me. So that's 50% of the class. But anyway, I think we can start the discussion of today's thing unless there are any other questions.
It's not well, ma'am.
Hmm? Okay, so basically, this is completely taken from your book. And it talks about how a compiler can, do some interesting smart stuff to ensure that the CPI is reduced, right? Clock cycles per instruction, that is your basic performance parameter, right? Rukma ma'am long ago told you about various basics of quantitative techniques, and CPI is one of them. So now this is the C code that we, is taken as a and essentially adding a scalar to every element of an array. Okay. And there are certain assumptions that are made. R1 has the address of the highest element initially, register R1. So register F2 is the scalar that has to be added. And R2 contains the address of, the last element, you can say, or past the first element. So you stop your loop when your R1 value and R2 value are equal, right? So that's basically the thing. So you load the last element of the array into F0, add F2 to F0 and store it in F4. And then you do the store, instruction to store it back into the array. Decrement the address so that you go to the next element of the array, and then if they are not equal, R1 and R2 are not equal, that is, you have not finished processing the whole all the elements of the array, you go back to the loop. So you basically take the branch here. When you say BNE R1 R2 loop, you are taking the branch. When they are equal, then you go to the next sequential instruction. Okay. Now, these are the latencies that are assumed in this example. And latencies are basically, when do you finish an operation and when can the, the number of, okay, between an FPALU operation and another FPALU operation. So you start a floating point ALU operation, and you have another FPALU operation. How many cycles are needed before you can use the result of the first one in the second one? That is the latency. So that is 3 cycles. Between the FPALU and store, it's 2. Load double and FPALU is 1, and load double and store double is 0. Right? Okay, so these are the latencies that are used in this example. Now let's see what happens if that is the case, right? So let's look at our example, load followed by an add, right? So load followed by FP operation requires 1 later all. Between an add and a store, So basically between an FPALU and the store double, there are two latency. I mean, the latency is 2 clock cycles. So you have 2 stalls after add before the store. Then you have your deadd, which is basically decrementing the address. But between a regular integer operation and a branch, they have, okay, I think it's not written here. Yeah, he also writes here in the um, caption, we will continue to assume an integer load latency of 1, right? And an integer ALU operation latency of 0, okay? And between DAD UI and DNE. They have a, maybe in the book it is there. But between the DAD and BNE is having a stall, which means that he assumes the integer addition takes 2 clock cycles probably. Okay. So then the above code takes 9 clock cycles for one iteration. This is the unscheduled pipeline code. You have done pipelining. However, each iteration requires 9 clock cycles because of the stalls, right? So now if you do some smart scheduling, that is after load, you bring the DAD, then so this is where, like, like this is similar to your delayed branch. You move your instructions around if there are no dependencies. Once you load, I think there is something, there is one mistake here in this slide also. I would say the store D should be 8 of R1 because we did a DAD UI R1 minus 8. We are supposed to bring an element of the array from the memory into the register, modify it and store it back into the same location. But if you look at, you did a load, so you brought an element, decremented the address of the next element when you did the DAD UI. But your store should not be going into that. Therefore, your store here should be 8 of R1. Okay. Please note the change. I'll make these changes and load in the Moodle. DAD UI immediately after load, your is there. Your slot instruction, which has no dependency on the load. Okay, so you avoid the stall. But after that, you have 2 stalls, and then after store, you are basically again doing the branch. So by doing a simple move of DAD UI and adjusting the address of the store, then we are able to reduce the number of stalls the number, of it works. I'm unrolling loop. This is what the code looks like. After that, we have to look at how many stalls will be there, how do you schedule the instructions to reduce the stalls and so on. Different iterations in one single, so you do 4 iterations in one loop, iteration sort of a thing. So the number of overall iterations will be reduced by 4. Okay, so you load, then you add, you store. Now when you do the next load, you are doing -8 because you are now referring to element last -1. Okay, and so on. So, and you also please notice that we are not using the same um, register to load into. Here we use the register F0, here we used F6, here we used F10, F14. Okay, similarly for add we are using F4 and F8, F12 and F16. But if we don't do that, okay, if we are actually using the same register, then we won't get any advantage out of this loop unrolling. We have to use different registers, otherwise what happens? You will have hazards, right? If you are using the same register, you'll have a write after write hazard for add, and therefore you'll have to anyway install add.t. You cannot do them simultaneously or concurrently, not simultaneously, but concurrently. That is, if you fetch one add, in the very next cycle you cannot do the other add because they're both using the same register. Okay, so that is why the register values are the registers that we use are different. And also we modify the way we do a DAD UI because now we are manipulating 4 elements in one iteration. So the register value of R1 is adjusted accordingly. Now, without doing any scheduling, okay, it will have a lot of stalls, no doubt, just as earlier between load and add, you have a stall, between add and store, you have a stall, and so on. Even though we have all that, it still runs in 27 clock cycles, reducing the number of clock cycles per iteration to 6.75. Okay. Now, by doing a different all adds coming together, because now by the time the add instruction comes into the pipeline, the load corresponding to it would have finished anyway. So there need not be a stall. And between add and store, you have 2 stalls. So if you have 4 adds, so by the time the store comes, your add has finished and written the result into the register, so the store can take it and put it into memory. No stall is involved. And because there is a stall between DAD UI and DNE, you move DAD UI a little before. So you do 2 stores, have the DAD UI, and then you have the next 2 stores. Now doing this will bring down the number of cycles needed per iteration to 3.5. Okay. So that is basically the advantage of this entire loop unrolling, right? By unrolling and scheduling, we are actually eliminating stalls and therefore bringing down CPI. That's the whole point of this exercise. Any questions on that? Okay, so to do this loop unrolling, we need to satisfy certain conditions. So the loop iterations must be independent. You can't have the value of one iteration dependent on the value generated in the previous iteration. And if that is the case anyway, there is a data dependence, the raw hazard comes into picture, and you will not be able to eliminate too many stalls in that case. But if they are independent, you will be able to do the loop unrolling. The most important thing is to avoid name dependencies. use different registers for different iterations. Like I pointed out, the load was into different registers, add output was into different registers. If you didn't have that, then there would be output dependencies, which is one of the forms of name dependence, right? So that there would be write after write hazards, write after reads. Those need to be eliminated. So you make sure that the registers you use are not the same. Okay. Eliminate the extra test and branch per iteration. So instead of doing a test and branch per iteration, now you are doing test and branch for 4 iterations. Number of branches, which is really very important thing to do. You are reducing the overhead associated with therefore to improve the performance. Now, the other thing you can also do in our exam, some cases, we did do this. Can you, can you interchange loads and stores? So we did interchange loads and stores. We should have done S dot D of 0 code before we do the second load, but we have simply interchanged loads and stores. Now, this is possible only if the loads and stores are, referring to different memory locations. If they are referring to the same address, obviously you can't, interchange loads and stores, because then you actually result, it will result in raw or war hazards in memory, not in registers, but the raw or war hazards in memory. So you have to make sure they are interchange loads and stores. Now schedule the code dependencies, right? You basically, you make sure when you are scheduling the code that any true data dependencies are preserved. Otherwise, the code will be, generating wrong answers because the logic changes. Okay, so these are the necessary conditions that we need for loop unrolling. Now, why is it that's not used as much? It is used, but not a lot. The reason is that, as you can see, when you increase loop unrolling, as you increase, that is, we have unrolled it 4 times. Instead of unrolling it 4 times, we do it 8 times. Then the reduction in overhead will not be as much. Okay. So it's something you hear about this everywhere in the world, right? The diminishing diminishing returns over time, right? So similarly, if you do too much loop unrolling, then your reduction in overhead is not actually in as much as would be in the beginning. That's one thing. Size obviously of the code increases, right? Because now you have so many instructions which you have to write, and so instead of writing 1 loop iteration, you're writing 4 loop iterations. So obviously the code size increases. Now the most important problem is that because we have to avoid name dependencies, the registers have to be different, which means that you need large numbers of registers. If you don't have enough registers, you won't be able to do enough loop unrolling. And even with reasonably good number of registers, if you do too much of loop unrolling, all registers may be used by your unrolled loop, and some of the values which need to be in the registers may be kicked out because of that. And therefore, now you actually probably end up having more fetches from memory into registers than if you were not doing loop unrolling. And this is called register pressure. And that is one of the most important limiting points for loop unrolling. So we can only unroll up to a certain point. Okay. So what is it that what are the lessons we can derive from this? We can unroll and schedule loops to reduce the CPI. However, to do that, we have to satisfy certain conditions. However, unrolling beyond a point really creates problems in terms of port size, register pressure. However, it's a simple technique to uncover parallelism between instructions within loops, where when we use even what are called as superscalar processors, that is where more than one instruction is fetched and issued in every clock cycle, right? So that is basically about loop unrolling, a very simple compiler technique to uncover instruction level parallelism that can be used by processors to improve the CPI. Okay. Any questions on that? Because that finishes what I wanted to talk about today. But after we come back, I think we will soon be running out of time. When we come back, just want to talk about what's the plan for the next class. Okay. I think we have we have 5 minutes left. If there are no questions from people, think about it. Let's leave and rejoin maybe, so that we can discuss without interruption up to 3, and then we'll be done. So my time says 2:37. Maybe by 2:40 we can join, and right.
Okay, ma'am.